Okay, well, I'm going to jump back in. So the second piece to this puzzle of finding insider threats is to, first detect what's normal, and then we want to detect when something unusual happens in the context of normal behavior, because most insiders try to continue to look like normal behavior and then slip in a few things that hopefully won't be seen. So real simply, but a real high overview of what we do for anomaly detection is that we first identify the normative pattern, which is essentially what you just saw. That's kind of what SUBDUE does. And then we feed that normative pattern along with the original data into a system we call GBAD for graph-based anomaly detection. And then that is going to output an anomaly. But again, the anomaly is basically an unexpected deviation to this normative pattern, not just a kind of an outlier or noise that's in the data. And the way we do that is we take this normative pattern and its instances, and we look for instances that are close to this one, like this instance here is close, but it's of course missing an edge. And so in that case, we would identify that as an anomaly and or output it. So there's two kind of factors that go into something being an anomaly. One is that it's close to the normative pattern. So we need some measure of closeness, and we use what's called a graph edit distance, which is basically what are the minimal number of changes I need to make to this graph so that it's equal to that graph. And so in this case, it would be adding one edge. So it's pretty close. Whereas if I chose another graph, like say that one, that would require 6 edges to be added and 5 more nodes. So its graph edit distance would be very large. And so there's a threshold that's defined. The user can define it, but we have defaults for it that work pretty well. And then the second question is, how often does this happen? Okay, we found that it's missing the edge, but maybe that happens a lot. And so we compute the probability of this deviant pattern given the rest of the graph and the normative pattern. So basically, we would say it passes the graph edit distance or the distance, but if we saw a bunch of these in the graph, then we would say, well, this isn't an anomaly anymore. This is actually a fairly normal behavior. And we see a lot of these cyclic patterns, and we see a lot of the cases where it's missing one of the edges. And so we compute the probability basically as the number of times we see this divided by the graph, the size of the graph, or the number of instances total, and make sure that probability is low enough. So this is saying it's close to a normative pattern, but it's still unexpected. And those are our two kind of definitions of what an anomaly is. So jumping right into exercise 2, we're going to run GBAD on a different graph. But first, there's a few nuances to the input format. So first of all, the input to GBAD is typically a set of graphs. It could just be one graph, but usually it's a set of graphs. And so we give each of those graphs a number. So we start out the graph with this XP, followed by the pound sign, followed by the number. And then, inside of that, each graph is defined the same way we did before. The only slight nuance is that for some reason, GBAD requires quotes around every label. SUBDUE only requires them if you have white space in it. GBAD was developed by one of my PhD students from long ago, who is now at Tennessee Tech University. So you'll see that logo popping up. So he's kind of the expert in the anomaly side of things. Yeah, so obviously we have a second example here where we find out that Jane owes John money, and Jane works in the IT department, and if John is up to no good, he might pressure Jane to give him access to something. So that's kind of where we're headed with this problem. Okay, so the next few slides are just the instructions that hopefully you have in front of you. So I'm going to jump over to the laptop. So now we're going to be getting this gbad.zip. We'll unzip it. Okay, so again, this is the let's see, I guess I have it on the screen. So the main website for GBAD is called gbad.info. And so if you go there and download the code, this is what it looks like. So it's clearly research code. It's got it's toolkit 4.0. If you go inside that, see a couple of different versions. This is a version of GBAD that uses a frequent subgraph miner, not a highly compressing one like we do. But GBAD MDL is kind of the one that we developed. So that's where we'll be spending our time. And also, there's some sample graphs in here. The one we'll be running is this example. So you can see the format as we saw before, and let's see. Yeah, so obviously you could stare at this and try to find the anomalies, but one of the anomalies is going to be this added vertex V here, and so you'll see that pop up as the anomaly. But first, we'll need to compile it. So I'll go to this GBAD MDL. And then inside the source directory, same thing, we'll type make, which will build it. And then make install, copy the binaries over to the bin directory. So then I'll back up one. Now, the GBAD over the years has evolved. We used to look for specific anomalies, like anomalies where there's something missing, anomalies where something has been added, or anomalies where something has changed. And so there's actually different ways you can run GBAD. You can run it with -add, looking for anomalies that are additions, -del, anomalies that are deletions. But eventually we figured out how to combine those all into one. So you can say the -all, but this requires a numeric parameter. And I think for this example, I chose 0.5. So what this means is saying it's basically a limit on how far the anomalies can be from the normative pattern. So if you remember that example, that cycle, the anomaly differed by one edge, which was about an eighth of the pattern. So that would clearly meet this criteria. This 0.5 basically says that no more than about half of the normative pattern can change for the anomaly. And so this is a bit of a tuning parameter. In fact, I think I got it down. You could choose anywhere from like 0.3 to 0.8, and it still works. But it basically allows the user to say, I'm only interested in anomalies that are very close to the pattern, or I'm willing to entertain anomalies that are very different from the pattern. So that's something you have to choose. And then the graphs directory is back up one. I'll just go ahead and I think in the instructions, you can, I'll go ahead and save the output. So here's the output. It first starts out by finding the normative pattern, which in this case is these 4 vertices and 3 edges. We'll visualize it in a second. Oops. And then it looks for anomalies to that pattern. So here it finds one of the instances of the normative pattern almost, and it indicates where the anomalies are. So there's this strange label on the vertex and an edge that wasn't there before. So that's kind of a textual output of GBAD. And then to visualize this, GBAD is nice in the sense that it visualizes the entire graph. It colors all the normative patterns blue, and then it highlights all of the anomalies in different colors. So we don't have this two-part, 2 different images. But we have to run GBAD with the output parameter. So it produces a dot file directly. So I'll just call it output.dot and give it the graph. Okay, and so then last I'll convert that file to an image. Let's see what it looks like. Of course, you have the picture in front of you. Okay, so here's the output. So you can see that there's basically 4 exact matches to this normative pattern, which is 3 vertices, or 4 vertices, 3 edges. And then here's the anomaly over here. Try to blow it up a little bit. So this is the normative pattern in orange here, but here's the extra stuff that we didn't expect to be there. So again, it's learning the anomaly in the context of the normative pattern. However, it also finds a couple of these normative patterns that have this extra edge to a 5th vertex, but it doesn't flag that as an anomaly because it occurs often. And therefore, its probability isn't low enough to be considered one of our anomalies. So that's basically how it works. It again finds the normative pattern, basically using subdue internally, and then it identifies the anomalous versions of the normative pattern and then indicates what the anomaly is. And does it in really nice colors. Okay, so back to the slides. So what have we done with GBAD? So just a couple of examples. So you might, maybe you don't remember Enron. Enron was a utility company that basically was hiding major losses. And there was an insider, in this case, I guess you wouldn't necessarily view it as a threat. There was an insider who was trying to essentially leak the information that this company is going down the tubes, but nobody knew it. And so obviously from the company's perspective, they didn't want that information leaked, but from investors' perspective, they do want it leaked. So insider definitely, threat depends on your perspective. But in the court case for Enron, for some reason, the judge required them to release publicly all of the emails that took place over the few months that this happened. And so CMU packaged them up really nicely for us, and you can go get all of these emails, complete with content, which is rather rare. And so our idea was, we're going to see a lot of normal emails, but we're going to see an unusual email, perhaps, that would identify who this insider is. And so if you do that, so I guess it's a little blurry, but this is basically whenever somebody emails somebody else, we get a link between those people. And then there's other links for if they reply. In some of the versions of this, we would include information about the subject of the email. But when we do this, we feed this into GBAD, it basically identifies this email from a vice president to an accountant as something that it didn't expect to see, in the context of all the other meetings. Because vice presidents usually don't email accountants, it's usually the other way around, or vice presidents are emailing other vice presidents, accountants other accountants. And so it turned out that this accountant was the whistleblower, Wanda Curry, who exposed the fact that Enron was in a lot of trouble. So obviously, from the company's perspective, we would want to get rid of Wanda. From the investor's perspective, Wanda's a hero. So, but either way, she was an insider that was doing things a little differently that we could have caught. Another application, there's a conference every year called VAST, which has to do with visualizing data. But they have a challenge every year. And in 2009, their challenge was to catch an insider who worked at an embassy and was leaking information out of the embassy. And I guess without going through, here's the data is available here if you want to play with it. But what it came down to was tracking the badging in and out, people badging in and out of buildings and classified areas. And eventually we found out that there was one person who went from outside to inside the building and then suddenly was in the classified area. So there's no record of them badging from the building into the classified area. They badged out, but they didn't badge in. So that was kind of the red flag. Obviously lots of people are badging in and out, but this particular one was missing the badging from the building into the classified area, which in the context of the larger pattern was pretty easy for GBAD to find. So synthetic example, but a good example of the kind of thing we can catch. Some other examples, so CADA, let's see, Center for Internet Data, I can't remember the name. But they basically collect a bunch of data about the internet, and one of the data sets they collect is basically the routers that are connected. They're called autonomous systems, and so you can track how these routers talk to each other, and so you can find this normative pattern, which is basically this provider-customer relationship. But then we found one case where one of these autonomous systems had two provider links to another autonomous system. And it turned out that this was, I believe it was a denial of service attack that was going on between those two routers. So, not something that you would ever really see when there's millions of these things to look at, but it definitely was an anomaly to the normal pattern that you can see. And the last example, which is actually the one you saw before, this is that government ID or passport office. And we looked at, I think we've seen this one where the frontline staff was doing a review of a case, which was not allowed for frontline staff. And we also they identified 7 other breaches that took place. And so we were trying to, of course, find all of these. I think this is number 4, where the approval officer reverses the recommendation of the case officer. So the case is kind of blurry, but hopefully you have the slides in front of you. So the case officer is recommending reject. You can't see it there, but then the approval officer is recommending an accept. Now that's certainly possible that the approval officer would decide not to follow the recommendation of the case officer, but it's very unusual, and it's in this case worth looking at as to perhaps the approval officer was compromised in some way for this particular person that's trying to get a passport. So I'm going to do one more exercise where we'll run GBAD on this document processing graph, and we're going to go after this second one here. So the frontline staff submits the case directly to a case officer, which they shouldn't do. The frontline staff gives the case to the approval officer, and the approval officer assigns it to a case officer. But in this case, the frontline staff go around the approval officer, perhaps trying to get a favorable case officer to look at the case. And what we'll see is that, so here's the normative pattern that will come out, which is the same pattern that we just saw, but then we're going to see this anomaly. And so here's the case where the frontline staff is assigning the case to a case officer, not the approval officer isn't doing it. So in this case, we're kind of missing this edge, and we have this extra edge. But it's the missing edge really that is the anomaly here. That's why this doesn't show up in red, is that it's really the fact that the approval officer isn't assigning anything to the case officer, which is the anomaly. So to do this exercise, I'm gonna, so here's the instructions for getting the results. When I run it on this AWS virtual machine, it takes 9 minutes to run. So I don't think you want to wait 9 minutes for this to happen. But I've already run it and I have the results. So I'll go ahead and show you that. But if you want to start it up, and it should finish before we're done. So here I've already run this before, so I'm going to go to a different directory. It has all of the same code as what we've been working with. It's just that I already ran it on this graph. So you can download the graph from the website. It's this ID process 2 graph. And I can show you a little bit about what it looks like. So here's what the file looks like. Again, it's got these XPs. The // is just a comment, which is an artifact of the generator that generates this data. But you can see, all of the different players the document request, and then all of the different processes that go on. There's actually another version of this where all of these are time stamped, and so you can actually find anomalies in the order in which they happen. But just keeping it simple here. So this is the output. So again, I ran GBAD. I ran it with that same 0.5, dash all 0.5, and sent the output to this dot file, ID output dot, and then I used the in this case I used a different program called SFDP. Instead of dot, I used SFDP to generate the graph because this graph is so big that it was crashing the dot program. But the SFDP is more efficient for large graphs. But yeah, all those instructions are in the notes. So I'll try to open this. It's not going to look very nice. So there were 1,000 cases in this. So you're looking at 1,000 cases, and you can kind of pick up, there were 3 anomalies, these orange spots here, which is where the frontline staff assigns the case directly to a case officer. Unfortunately, if you zoom in, the nodes are so big that it kind of obscures everything else, but I'll try to zoom in a little bit. So again, that's that anomaly. You already saw it, in its more pristine form. But obviously, if you just take a step back and look at the graph from high up, you can immediately catch where the anomalies are, and then of course you can probe in. So for some reason, when I run the SFDP on this Linux VM, it generates this mess. But if I run it on my Mac, which I was doing earlier, this is much cleaner. And so let me show you that. You don't have this. So it's pretty big graph. So this is what I get when I put it on my Mac. And again, you can see that the 3 anomalies are over here. And if I zoom in, here when we zoom in, we get a little better picture. Over to the side. So here's one of the anomalies here. I think there's 2 more. So assuming all of the visualization works out, this is the kind of response you would get, and then again the anomalies kind of jump out, and then you can dig down and kind of figure out what is different between this and these normative patterns. So that's a more realistic example of running GBAD. Obviously, taking 9 minutes to run is one of the challenges in graph algorithms, but clearly we could speed this up if we ran it on better hardware or parallelized it, etc. Okay, so almost done here. Okay, so again, in the notes, this was the example we just saw. So that's basically it in terms of the basic algorithms we run to find these patterns and anomalies, which many times can uncover these insider threats. As you saw from the first slide, the breaches are only increasing, as is their cost. But most of the current approaches, again, are usually statistical in nature. They look for one particular feature or dimension of the problem, like what time of the day or what day of week does a person normally access the systems, and when that changes to something unusual, they raise the red flag. But we would say, no, not yet. We need to see the context of what happened here. Why did Larry access the systems from home on a Saturday? Maybe if we add more context about again, a big presentation on Monday, then that wouldn't seem quite as anomalous, because we've seen other situations where that happens. Again, the two main tasks that we have is to first find the normative patterns. And then once we have the normative patterns, we look for anomalies, which are the close unexpected deviations to those normative patterns. So what are the challenges we're dealing with right now and kind of always? One is, how do you represent the data as a graph? So back to so this example. We obviously we have information about who knows who owes money to who, what department people work in, but maybe you want to represent it a different way. So maybe you instead of just owes money, you want to know how much money. So you might have another vertex here, which is the owes money vertex, and we could say person one owes money to person two, and there'd be another link coming off with the amount of money. Maybe the department, IT, we want it to be an attribute of this node and not a separate relationship. So there's a lot of decisions to make into how you represent the data. And basically, there's an infinite number of ways to do it. But basically, you have to think about, what am I after here? I'm after trying to identify people that are doing something close to what they normally do, but it's a little bit different. And so, with that goal in mind, that usually guides you as to, is owes money an attribute of Jane, or is it a relationship between Jane and John? But a lot of times you have to iterate over a few representational choices to get it right. So that's a challenge. As we see right here, that document processing graph, I believe, is about it's like about 5,000 nodes and about 10,000 edges. That's not a very big graph, 15,000 nodes and edges, and it takes 9 minutes for us to process that on a reasonable hardware. And as you saw from the beginning, we get into graphs like monitoring the internet or web or social media. that data just keeps getting bigger and it keeps coming in faster and faster. And, so we're constantly having to back our algorithms off from optimality to get them to finish fast enough to be able to react to what we find. It's not very interesting if we, find out tomorrow that somebody did something yesterday that we should have investigated. And another challenge is, there's basically infinite amount of data out there. And when you start thinking about, so what could cause Jane to become an insider threat, the sky's the limit. It's all of Jane's emails and her financial transactions, her relationships outside of work, you name it. Where did she travel? Did she travel internationally? Where? Because all of that data could potentially impact whether Jane is an insider threat. But you have to draw the line somewhere. We can't just take all the data in the world and stick it in this graph and expect us to be able to find anything in a reasonable amount of time. So, there's lots of challenges in fusing the data. For example, we can analyze individual data streams, like Jane's financial transactions. We can look for anomalies there. And then Jane's relationships, we can look for anomalies there instead of fusing it and having to deal with the larger graph. So there's some tricks we can do to try to make it more efficient. But in the end, we want as much data as we can to inform these kind of searches, but we don't have the luxury of using it all. Okay, so that is the end of my presentation. Thank you for your attention, and I'm happy to take questions. Yes.
Who and how is normative our normative patterns established? Like get contracts with companies, they tell you want this done for this year's time frame. Is that kind of how that's, or do you have a time duration or a system now?
Well, the normative patterns can come from two places. One is the company can tell us these are the patterns that we see, or if it's a pretty mature company, they actually have policy documents for how all the departments should work and interact with each other. But generally, we don't want to depend on that because we would rather just get the raw data and in an unsupervised way, we allow our system to figure out what's normative. So that way, if a department is doing something that's different than what the company is telling us they're doing, but it's still perfectly reasonable, then we can find that normative pattern. And sometimes it's a surprise to the company saying, "Oh, I didn't know they did that, but that's actually a better way to do it," or something like that. So we can actually input normative patterns and say focus on these. But we tend to like for the system to find the normative patterns itself, because a lot of times they're different than what people expect.
I got one question. With GBAC, I don't know if it's familiar, but with GBAC threat detection software that they developed and
not that I'm aware of. I mean, we didn't have any contract with them to work on it. A lot of times we get data from a company, and the hard part is figuring out the representation, and then we run a few trials, and then they take it from there, because they would rather run everything in-house, and they don't tell us what the results they got. There's another bad thing about insider threats is we probably only know about 10% of the ones that are actually going on, because companies don't want to tell you that bad things are happening.
Got a question for you, Larry. What about what do we call this software? Workday, sort of the software that WSU uses. It seems to me like the software only allows certain conditions, and so there's a lot of checks and balances on somebody not doing something correctly that can be done. But are there things that you could monitor with Workday that would reveal hey, somebody's bypassing the system or something.
Yeah, I mean, a good example would be, another faculty member, say a co-PI on a grant. I say, I'd really like to see the budget information, but I don't have access. And you say, well, here's my login and password. Just don't tell anybody, and you can go in there and look. And I do it in a way that you've never done it before. Maybe I bring up spreadsheets that you've never done. I access it at a time of day when you've never done it before. And, like a system like GBAD could detect that. And then you probably get an email or phone call saying, did you really access the system at this time? So I think that's how it could work. But of course, there's privacy issues of accessing all that data. And at this point, WSU hasn't allowed us to do that. So.
Yeah, there's a lot of access limitations. I suppose somebody could hack in, check grades or something like that.
Yeah.
Or somehow get your ID. That's what.
Yeah, a lot of insider threats that the insider does something, stupid, but they're not really the insider. It's somebody else, standing in line next to them at Starbucks is, looking over their shoulder at their ID or ask them, what's your mother's maiden name? I think I went to high school with her or something like that. There's lots of social engineering that goes on to give them that access, and then
I suppose with two-factor identification, it's hard to bypass the system. Unless the intentionally involved.
Right. Yeah, the bane of our existence.
Yeah, so the big push for zero trust architectures coming out. And you see this as a big push for that as well. They're going to concern with that policy. So we now no longer have an outer boundary in our networks that we don't trust anyone. So it's lost again. We have no trust. And so I didn't know if this would either toward that or help out in that extent.
I guess, I don't have a lot of knowledge about that, but I think our approach is a zero trust. I mean, we basically don't trust anybody, and but we let the data tell the tale. So, if they're sticking with their normative patterns and they haven't been a problem in the past, then we would tend to not be suspicious. But as soon as something unusual happens in the context of their normal behavior, we would immediately be suspicious. So trust but verify, I guess. All right.
Yeah, Larry, another